right? So it looks like this. The VDD. That's V in, that's V out. So that's a gate dielectric material, so nothing is being physically connected to it, right? And that's the input capacitance for the PMOS, NMOS. It's definitely RP, channel resistance for the PMOS, channel resistance for the NMOS. So just let me know what is this capacitor is. Yeah, I haven't split it, right? If I model it, then it becomes 1 cox. But now physically it is still this, right? So we got a half cox here, which has a mirror effect. So this is, you know, in the real world, this becomes 1 cox. And what is this one? Oh no, sorry. This is not changing. This one doesn't have a mirror effect.
So which one is that in the model? Is the first one on the top?
Let's just directly write the ones has a mirror effect, all right? So the final capacitance value. It's not confusing. So this one is tied to the VDD, so it's not changing. Whenever this one is changing, the other side of the cap is not changing, right? So this one doesn't have that mirror effect, but this one does, because when this one is charging, this one is discharging. So this one should be a half cox, but in real world, because of the mirror effect, this becomes one cox. Okay. So what is this one? The model. 3 halves, right? Yeah, combine them. There's just one, right? Cox P, right? Yeah, same to the NMOS. And because of the mirror effect, as the output, this capacitor is being divided into 2. One here is for 1 cox P, and the other side is another cox P. This is cox N for the NMOS. Any questions by far? So this one is a half cox P, right? If you divide it in 2, and on the 2 sides, each one has mirror effect, so it becomes cox P and cox P. So we're getting cox P here and cox P here, and this one becomes 1 cox N, and as the output is another cox N, so cox N and cox N being added to the other half of cox N here as an input. So that's a digital model for the inverter, for one inverter. Okay, if you have multiple inverters, just connect them together to find out what are these capacitors being involved whenever it's being toggled, and what are the resistors being involved. A very quick review on the ones we covered on Friday. And ring oscillator. So if I have an even number of inverters being shorted together, like that, why it won't oscillate? Why stable? Yeah, it's even. So for example, at a moment, this one has a rising edge, right? And after a certain amount of time delay, it shows a falling edge, and then rising edge, then falling edge, then rising edge. It's still the same thing, the same wire. Yeah, just a wire. Same signal, so it's not oscillating. Or you can say, you can test it using this way, right? 0, 1, 0, 1, 0. Stable, like latches. So you have 4 inverters is same as 2 inverters, right? Just 2 bigger inverters. Right, the 4, if it combines these 2, if I have a 6, you can combine the 3 of them, right? It's like one bigger inverter and connect to another big inverter. And this is a latch. And why is this a latch? Because it's stable. Why one inverter is not a latch? Switch, right? If I turn on the switch, so it doesn't matter what is the voltage for in, it can be 0, can be 1. It's getting an output here. It can be 0 or 1. If you got a 1, you got a 0, 0, 1, right? But if you open the switch, can you still get any signal? Is this one storing a signal? Is it able to store any voltage in there? It's not a latch. It's not able to store anything. If you open the switch, you do the simulation LT-SPICE, it's not going to show anything. And you are thinking, hey, you got caps, right? Why the caps not storing all the charges? Yeah. Yeah, because you don't have any input here to turn it on or off. It's lower than the threshold voltage. It's just not doing anything. But if you have 2, like this one, right? So this one is the same as and now if you got an input here, switch, why is different? So my question for you here is, if you have one inverter and you open a switch, so the answer is you're not getting anything, right? If you probe it, it can be 0, but you don't want to say 0 because it's not ground, just a floating wire without anything, right? Couldn't say 0. Yes, if you probe it, it's going to be 0, but you just couldn't say it's not a strong 0, right? 0 and nothing is different because 0 volt is considered as ground. It is able to discharge a lot of things. But it's a floating wire, it's not, if you probe it, 0 volts, it's not 0. Okay. What about this one? If I close the switch, definitely you are going to see something, right? Depends on the switch. It depends on the input voltage. Right? If you close the switch, for example, you got a 0 here, 1, 0. It just keep going. It's a positive feedback. Or it's a latch. It's storing 0 here and 1 here forever. And then at some moment you open the switch. Are you going to lose the data? Why? Yeah. What's happening internally? What's happening inside the transistors? So this is 1, right? Yeah, before you open it, right? Like the example we had, I had a 0 here. Okay, so 0 means it's going to open the PMOS. So it's like opening this wire here, and so the charge is going to flow to this point and charge it up to 1. Okay, and this one is going to turn on this one and pull it down to 0. Because these are, as long as you keep the power on, just don't unplug it. Just keep it on. VDD, keep it on, right? That's going to be a latch. Huh? Good one. It's going to store the data, right? So that's why this is called a latch. You'll see different versions of this one. You know, 2 inverters like that, or sometimes you'll see somewhere else, it's being drawn like this. It's also a latch. It's a memory. Yeah, why not? It just does the job. Okay, it's for transistors. And sometimes you'll see it's being drawn like this, but still the same thing. So usually the memory cells are being drawn in this way. Is the same thing? Yeah. Yeah. Or oh, it doesn't matter. It can be here, can be here. There's just two nodes, right? 1, 2. It's 1, 2. And you'll see something like this as well. Let's see how we do it.
Oh yeah.
Yeah.
Just because you can.
Oh, I'm just showing different versions. Whenever, because if I just draw this, sometimes you'll see something like that in a different textbook. You won't be able to know like it's a latch, right? It's just not intuitive enough. So these are all the 4 versions you will probably see anywhere. Hopefully you know they're the same thing. Right. Latch, delatch. Same, right? Okay. Good. And then what about the odd number of inverters? It's going to oscillate. So let's see how many are here. 5. And why it oscillates? You can do 3. Yeah. And why is this oscillate? Oscillates, sorry.
So then it just continuously changes.
So for example, there's a rising edge happens at some moment here, right? That's gonna do this. So it becomes different, but why it oscillates? Because every single gate will introduce a little delay, time delay in there. So whenever this one has a rising edge, it takes that delay and then do the falling edge. So it can oscillate. Yeah, the frequency can calculate. I'm going to show how to calculate it, but you understand why it oscillates, right? So it takes some time, falling edge. Okay, and then this one becomes a falling edge now, here, right? Then it's going to do that. Show falling, rising edge again after some moment. All right, so it's going to keep doing that. So how to calculate the time delay, which is, if you know the time delay, you can calculate what? Yeah, the frequency of the string oscillator. Why that is important? Yeah, yeah. If you are trying to design a oscillator for the circuit, for integrated circuit, you want to know the frequency, right? So know what's the clock frequency. Internally, sometimes we use a ring oscillator to generate clock internally, but not for the clock from the crystal from microcontrollers. Yeah, that's the main clock from the outside circuit. You just solder that thing to the board and power it up, it's going to oscillate. 2 megahertz, for example. But For example, sometimes you couldn't divide the frequency of the original clock on the board to a frequency that you need for a certain part of the circuit. And you can have an internal ring oscillator. And also these ones can generate a super high frequency. In the range of gigahertz, a few gigahertz. Mm-hmm. And it's being used for, I think, a couple of years ago when I was reading some of the papers, they use the ring oscillator because they can generate a super fast clock as a shutter for a high-speed camera. Femtoseconds frame rate. Like,
would you use BJTs in that case instead of CMOSes? If you're trying to get a really fast inverter?
Are the BJTs slower?
Oh,
They're faster, but they take way away.
Oh, and if you have a camera, you would want that then. You fry everything.
I don't know why BJTs is faster, because the CMOS you can make it 5 nanometer FinFETs that are super tiny. You can charge and discharge it really quickly. But if you compare, I don't know if you can make BJTs that small.
So what's the point of BJTs?
Oh, they are being used for power electronics. It can, allows more current to run through, I guess. I haven't used BJTs too much, just in some of the circuits, but so probably my answer is wrong. I haven't even fabricated BJT on the chip. We always do CMOS, haven't done any BJTs. So we did the dials. I think for the chips you saw on the website, they have the dials, ESD dials, to protect the pads. So you can make dials on the chip, right? How to make a dials? Dial. Yeah, pin junction. Which first? Which first? No. Yes. Which is P, which is N? Right? So that's a diode, right? Yeah. Okay. How to calculate the time delay for this guy? That's simple, right? So from here to here, the time delay is called, it's high to low, right? And here is TP low to high, and TP high to low, and TP low to high, and TP high to low. That's for half of the period. And then do it again here, okay? High to low, then TP low to high. It's the same numbers, come on. Just calculate one. Okay, so T, which is, for the whole delay here and whole delay here, is just one period, on and off. Okay, so T equals all the TPs added together. And what are they? It's 5 times of TPHL plus TPLH. And this, the 5 is what? 5 is the number N, right? Like how many inverters they have in the ring oscillator, which is number N. So what's the frequency of the ring oscillator? Which is 1 over T. So that's how I calculate it. It's pretty easy. You just need to calculate 1 and 1, then times 5, 1 over the whole thing. Okay. So what is TP HL? Assume these are all the same inverters. Equivalent. So I sealed that number in your mind, 0.7.
Okay, and then the resistance,
HL is high to low is almost involved, right? Let me draw a second one for you. Like this, starting from here, right? Okay, so that's the node you're analyzing. Because here's this 1 times cox p. This is 3/2 cox p, 3/2 of cox n. Okay. So when you are looking at high to low, these are the four caps are always involved, no matter it's high to low, low to high, doesn't matter. But for high to low, the nMOS channel resistance involved. So it becomes Rn times 5/2. Oh wait, really? Oh, 5/2 of cox p plus cox n. So TPLH equals 0.7 times RP times 5/2 of cox p plus cox n, right? Any questions on this? Pretty straightforward. Okay, cool. And then
that's like a generic formula, isn't it? For all ring oscillators.
Why not? What's the concern here?
Like we can just use that TPHL for all ring oscillators, can't we?
I think so, yeah. Okay. As long as they are equivalent inverters here, right? You don't have the big ones, smaller ones. As long as they are the same thing, there's no difference. These are only parameters we have. Okay. So imagine that if you use a 5 nanometer, so here's the question, right? So if you want to design a very fast clock, high-speed clock, you want more or less inverters? Definitely less, right? So less inverter will give you less time delay, so you're getting narrower pulses. So you use the most modern technologies like the 5 nanometer technology, NMOS, PMOS, to form. Yeah, if you got more time here, it's faster frequency. Yeah, no, that's okay. Yeah, and if you use the 5 nanometer technology, the super short time delay, and only 3 of them, for example, I think it's gonna be like hundreds of gigahertz. So that's how you can form really fast clock signal by using this. I don't know. I think if you look at I think I search for high-speed cameras, see what's the newest cameras people are publishing. I think they have to use something like this to create the shutter signal. Dynamic power supply. How to calculate power or estimate the power consumption of the digital circuit. The inverter is just one example. You know, all the digital circuits are just 1 and 0s. They are charging and discharging all the parasitic caps or the capacitive lobes. So it's charging and discharging the cap. Okay, so how to calculate it? From the capacitor, I average, so average current going into and going out of the capacitor equals Q total over T equals VDD times C total. The period of the clock. Over T. So power average power equals VDD times I average, which equals VDD square times C total times F. It's not that accurate, but it's going to provide you a very good estimate of the power consumption of the digital circuit. So if you want to reduce the power consumption for the digital circuit, what are these parameters you can modify? Yeah, don't use 5 volts, use 1 volt. Right, 180 nanometer technology, we use 1 volt as a VDD. Okay, so you can reduce a lot of power consumption. And C total, how to change the C total? Smaller transistors. Remember the so all the gates are generating capacitance, right? If you use a smaller channel, if you compare a 500 nanometer to a 5, it's a huge difference. Probably, how do I draw that in scale? That's a 5 nanometer transistor. I drew it. Didn't see it, but I did it. Right? So it's reducing a lot of power capacitance. And power. So whenever you get a smaller transistors, you can run it faster. Like the 5 nanometer technology, we usually can run it a lot faster than the 180. So it's going to increase the power consumption. That's why when you integrate more circuits in the same footprint in the silicon die, and you can definitely run it faster because these are smaller transistors. So that's why it's introducing a lot of heating problem for the chip. It's the same area, but more circuits and faster clock. So they have to design, I don't know, there might be a lot of design strategies to reduce the heat in the same area. So just know that frequency is going to increase. If you increase the frequency, the clock speed, it's going to increase the power consumption here as well. Right? Okay. I think we're pretty much done for that part. 7 minutes. I'm going to show you a different structure of the D latch. The D latch I just showed you guys is a fundamental component of the clock, the D latch. And it's being used for D flip-flop. It's one problem in the homework 10. So this is a latch, okay? But if you want to make it into a D flip-flop, you have to introduce transmission gates in there. I know you hate this thing. Hmm? And here's a clock bar, clock bar, clock. That's it. So that's the D latch. And why is the D latch? So here's Q naught, and here's Q. So that's the data. Okay. What's happening here? Yeah, that's the transmission gate, NMOS and PMOS, right? So this is clock bar. So these are inverted signals being shorted to the AND gates, the two transmission gates. So whenever this is on, if this is on, and the PMOS, here's a clock bar signal, it's an inverted signal of the clock. So if this is on, what about this PMOS? Yeah, on as well. It's a trap. I'm waiting for you guys. It's off. Yeah, you want to keep both on in order to transmit the data over, right? So when this is on as well. But the entire transmission gate here is off because clock bar, right? For the most on off on. Okay, so if this is on, data will pass to here. You got a Q and Q naught. Okay, because when the clock is off, this one will be on, and this one will be off. So the inputting D is not affecting the Q anymore. It's a latch. So only on and off, right?
Yeah.
Let's see. On, off.
Yeah. Well, it's not oscillating. Or it's not.
No, it seems like.
It's even, so.
Why you need to clock it? Oh, if you keep this on, data comes to here. Why you want to turn it off when this is on? Because yeah, it is flowing. Is this going to affect anything here? If this is 1, right? If this is on, got a 1 here, got a 0 here, and 1 here. It's the same signal, right? It might be useful for the second stage because this part is used for being used in the clocked D flip-flop. I'm gonna draw it probably on Wednesday. We'll see if it's working there as some of the.
But the other, the non-clock people actually went over the feedback offer.
Yeah, so I'm confused.
If you.
Because there's current going this way, there's no current going back.
But if this changes, what's gonna happen? If this changes.
Then that's 0 there. Oh wait. 1, 0, 0.
It's okay, right? Because this point is being inverted twice. It's not going to affect anything or competing with this signal. But so if you keep this on, you are still able to charge and discharge this latch. So I don't think it's going to affect anything here.
Yeah,
but is this
you turn it from on to off, wouldn't one still be in the latch?
You want it to be that.
Okay, so then.
No, you're doing.
Yeah, you want it to start.
Okay.
Yeah, I don't think it's going to affect anything here.
Okay.
But is it going to affect anything else if we have two D latches being put together to form a flip-flop?
On the right that's changing your Q naught somehow, maybe?
No, not here. I think it's okay if you remove this one, it's not going to affect the results. If you run the simulation, I'm not expecting any difference. But if this clock is on, data comes here, so the data is ready. And then when the falling edge happens, it stores it. It probably just want to do it asynchronously. So rising edge samples and falling edge stores.
Oh.
If you don't have this one, then rising edge sample data passes through, right? But even you don't have this one, falling edge is still going to store it.
Oh, without that one on the right, would it be level trigger instead of edge trigger?
No, it's always level triggered
Oh,
because there's nothing, there's no switch here until here, right? So it's nothing.
okay.
And if this is on, everything will pass through to reach Q and Q naught. We'll see if it's going to affect anything for the D flip-flop later, okay? Good. Good question.